Welcome to the video lecture for section 12.2. This is for MSc 1105. My name is Jorge Gavillan, and this is college algebra. So we have four objectives. We're going to write the augmented matrix of a system of linear equations, write the system of equations from the augmented matrix, perform row operations on a matrix, and then solve a system of linear equations using matrices. So a matrix is simply defined as a rectangular array of numbers. We have row and column. So here, when we denote a place or one of the components, here the first value is the row and the second value is the column. So this is row 1, column 1, and then this will be row 1, column 2, row 2, column 2, all the way down to row M, column N. So we're going to write the augmented matrix of a system of linear equations. So here we have A and B. So A is two equations with two unknowns. B is three equations with three unknowns. Now, we have to take care to remember that here for equation number 2 and B, we're missing a y. In equation number 3, we're missing a z, and we have to compensate for those missing variables. So the first one is pretty straightforward. Here we write our variables, the coefficients, and then the results. For B, again, you got to be careful. So here's the original one. Obviously, two things. All of the constants have to be on the right side of the equal sign. All the variables on the left side. And so when we do that, we see that we are missing a y in equation 2 and a z in equation 3. So that's going to be 0 for all those. And you can see here the zeros and then all the constants on the right side. Next thing, we're going to write the system of equations from the augmented matrix. So here we have A and B. So A appears to be a system of two equations with two unknowns. B is a system of three equations with three unknowns. And so for A, if we assume that the variables are x and y, this will be the system of equations. For B, if we have x, y, and z, then this will be the system of equations. Next thing, we're going to perform row operations on a matrix. We can interchange any two rows. We're going to replace a row by a non-zero multiple of the row. We're going to replace a row by the sum of that row and a constant non-zero multiple of some other row. So in this example, we're going to apply the row operations. R2 is going to equal to -3 times R1 plus R2. And so what's going to happen is that our new row 2 is going to be equal to -3 times row 1. And then we're going to add that to row 2. And so here's our row 1 and here's our row 2. So we multiply the first one, -3 times the corresponding component, which is 1 here, plus 3. And then so in this case here, we get -3 times a -2 plus -5, which is the row 2 component of this row operations. And then -3 times 2 plus 9. Again, you can see all the components. And then we get a new row 2, which is 0, 1, and 3. So here you can see that we can actually create new rows by multiplying one row by a non-zero constant and then adding or subtracting it to another row. So here we're going to find a particular row operation. So find a row operation that will result in the augmented matrix. So here we have 0, -2, 2, 0, 1, 3. So having a 0 in row 1, column 2. So we want a 0 in row 1, column 2, so we want a 0 here where the -2 is. And so what we end up doing here is that R1 is going to be equal to 2 times row 2 plus row 1. And so here you can see 2 times my row 2 plus my row 1 will give me a 1. And in this case, 2 times, again, row 2, which is my 1, plus my row 2, plus my row 1, which is -2, gives me a 0. And then 2 times row 2 plus row 1 gives me an 8. Excuse me. Well, here we're going to solve a system of linear equations using matrices. So a matrix is in row echelon form when the following conditions are met. The entry in row 1, column 1 is a 1, and only zeros appear below it. The first non-zero entry in each row after the first row is a 1, only zeros appear below it, and the 1 appears to the right of the non-zero entry in any row above. Any rows that contain all zeros to the left of the vertical bar appear at the bottom. And so here we have a system of linear equations using matrices. So we have a system of three equations, three unknowns. We have equations 1, 2, and 3. And so first we write an augmented matrix that represents the system. So here's the augmented matrix. Step 2, we're going to perform row operations that result in the entry in row 1, column 1 becoming a 1. So to get a 1 in row 1, column 1, we interchange rows 1 and 2. Note that this is equivalent to interchanging equations 1 and 2 in the system. So step 3, we're going to perform row operations that leave the entry in row 1, column 1, A1, while causing the entries in column 1 below row 1 to become all zeros. So next we want a 0 in row 2, column 1, and a 0 in row 3, column 1. So when you use the row operations, R2 is equal to negative 2 R1 plus R2, and R3 is going to be negative 3 times R1 plus R3 to accomplish this. Now note that row 1 is unchanged using these row operations. Also, you see that performing these row operations simultaneously is the same as doing one followed by the other. So here you can see what we got. Now, step 4, we're going to perform row operations that result in the entry in row 2, column 2 becoming a 1 with zeros below it. And again, so this is what we want. So in step 5, we're going to repeat step 4 to get a 1 in row 3, column 1. And so here we got R3 is equal to negative 1/2 R3. So you don't have to necessarily add any rows to it. You can multiply a row by a value, and sometimes that just does it for you. So in this case here, row 3 becomes negative 1/2 times row 3, which is the new row 3. And then here, the matrix on the right in step 5 is in row echelon form. This is the augmented matrix. Use the back substitution to solve the original system. So the nice thing here is that we get that y is equal to 2. Right? We also get that, y is equal to negative 4z is equal to 10. That's row 2. And then, so we know that from the bottom, z is equal to negative 2. So we can go ahead and substitute that into our equation. And we get that y is equal to 2. So finally, we back substitute y is equal to 2, z is equal to negative 2 in the equation x plus y plus z is equal to 1, and we get that x is equal to 1. So the solution of the system is the triplet 1, 2, negative 2. So matrix method for solving a system of equations. Write the augmented matrix that represents a system. Perform row operations to get the entry 1 in row 1, column 1. Perform row operations that leave the entry in row 1, column 1 unchanged while causing zeros to appear below it in column 1. Perform row operations to get the entry 1 in row 2, column 2, but leave the entries in columns to the left unchanged. It is impossible to place a 1 in row 2, column 2. Proceed to place a 1 in row 2, column 3. Once a 1 is in its place, perform row operations to place zeros below it. Step 5, repeat step 4. And then step 6, the matrix that results is the row echelon form of the augmented matrix. And then we can analyze the system of equations corresponding to it to solve the original system. So here's an example. We have a system of 3 equations, 3 unknowns. So we're going to write it as an augmented matrix. And so the first thing that we did is R1 is going to be equal to negative 1 times R3 plus R1. And that gets us our second here in the middle. And then for the next step, R2 is going to be equal to 12 times R1 plus R2. And then R3 is going to be equal to negative 5 R1 plus R3. So obtaining a 1 in row 2, column 2 without altering column 1 can be accomplished by R2 is equal to 1 over negative 22 R2, and R3 is equal to 1 over 11 R3. We interchange rows 2 and 3, and then R2 can be 23 over 11 R3 plus R2, and then we get here the augmented matrix that we went of the row echelon form. Now, this matrix in row echelon form, because the bottom row consists entirely of zeros, the system actually consists of only 2 equations, which is equation 1 and 2. So to make it easier to write down some of the solutions, we express both x and y in terms of z. So from the second equation, y is equal to 1 over 11z minus 2 over 11. We back substitute this solution into y for the first equation. And then we get that x is equal to 2 over 11z plus 7 over 11. And then when we complete it, we end up with z is equal to negative 1, x is equal to 5 over 11, and y is equal to negative 3 over 11. Some of the solutions of the original system. Now, there are in fact infinitely many values of x, y, and z for which two equations are satisfied. So that is the original system and infinitely many solutions. Oops, sorry about that. So, let me go back. So we will write a solution as the original system. Here we have solving a system equation using matrices. We have 4 equations with 3 unknowns. So we're going to begin with the augmented matrix. We're going to perform these row operations to get to this middle matrix. And then we're going to interchange rows 2 and 3 to get to this matrix. To get to this matrix here, we multiplied R3. R3 is going to be -6 times R2 plus R3 from this one to get here, and also this row operation for R4. And then the last one, R4, becomes we do these row operations to get this augmented echelon row echelon matrix. So we can stop here since the matrix is in row echelon form and back substitute z is equal to 3 to find x and y. Or we can continue and obtain a reduced row echelon form, which is the last one here. So the matrix now is in reduced row echelon form. We can see that the solution is x is equal to 1, y is 2, z is 3, or any ordered triplet 1, 2, and 3. 12.2. Thank you.